Welcome to Inverse Trig.
Hey everybody, welcome to class. We are here to teach you inverse trig function today. My name is... My name is Cameron.
And my name's
Aaron.
Aaron.
And I'm Andrew, yeah.
All right, let's get started.
Oh, wait.
Hey everybody, I'm Cameron again. Welcome back, and I'm here to talk about cosine today. So the first thing that I'm going to show you is the cosine graph. Right here, we have one period of the cosine graph. Now, it continues on in a sinusoidal function, going this way and this way on the graph, and it'll just continue in its loop. But for right now, we're just going to stick with right here. What I'm here to talk to you about is how to change this into an inverse cosine graph. Now, the domain currently is going to be the domain currently is going to be all real numbers because it keeps going. So right there. However, as you can see by the range, it stops at 1 and -1. So that does not continue all the way. As you can see there. Now, when you change this into an inverse cosine graph, what you have to think about is flipping the x and the y's. You have to switch them in their positions. And on top of that, it can't be the same exact thing because there's something new called the PI, which is the principal interval. And for this, the cosine equation, the principal interval is going to be from 0 to pi. Okay. The PI. So, now this is the inverse cosine graph. And what's different about it is, once again, it flipped, and so now it's continuing, it would continue up. However, that would make it so it's not a one-to-one function anymore. So we had to stop it within the principal interval. And so the domain and the range flip, except now the range is what the principal interval is. So let's put that in. So here we go. That's the domain and range for an inverse cosine function. Now, I'm going to show you where it is on the unit circle. Here's our unit circle. This is going to be 0, pi over 2, pi, and 3 pi over 2, and 2 pi. So, the place that this goes here is from 0 to pi. And so whenever you're solving for an inverse cosine, you have to make sure that your solutions fit within the principal interval, or else there will be no output. Thank you very much.
All right, so here you can see the graph for y equals sine of x, and this is its beginning interval, but it extends past that, and so it has a period of 2 pi, and also its principal interval is from pi over 2, negative pi over 2 to pi over 2. So go ahead and fill that in. All right. And then as you can see, it has a pretty large domain, actually all real numbers domain. So you can express that two ways. You can use the all real numbers symbol, or you can say from negative infinity to positive infinity. And that's how you express its domain. And then its range is just from -1 to +1. So, and that is inclusive, so that is a bracket. So it's -1 to +1. All right, so that's sine. And now for inverse sine, it is a one-to-one function, and so that's why you have the principal interval over here. It's to restrict it to make sure when it's inverse, it has a one-to-one function. And its domain is from -1 to +1, which is the range of sine. And its range is now the principal interval of sine's graph, and that is -π/2 to π/2. And that is also inclusive. And then on the unit circle, its range is expressed from the bottom of the circle all the way up to the top, and so that goes all the way around. And so that is sine and inverse sine.
All right, go ahead. So, on this graph, including every period that we haven't written, the domain is everything except for the asymptotes. So let's write that over here. So x equals, or x does not equal π/2 plus pi k. Let me write that differently. All right. So that's the domain for these graphs, for this graph. And the range, as you see, as it approaches each asymptote, up and down, the range is going to be all reals. Okay. So that's our tangent graph. That's just the way it is, plus every period. Let's say we wanted to make an inverse tangent graph. Well, if we did an inverse with every period, it would not be a one-to-one. It would not be a function. They would be stacked on top of each other, which means that normally the tangent is not a one-to-one function. So we have to limit the domain enough to make it make the inverse tangent function also a function. So we call that the principal interval. So for this, as we see over here, on our inverse tangent graph, there's no extra periods above or below it because we have our principal interval. Let's write that over here. So our principal interval is from -π/2 to π/2 as in the period we've drawn. That's not how you write that. And again, these are not including those values because they're asymptotes. So, as you see over here, our principal interval, our whole graph is now inverse. The x's became the y's, and it's flipped that way. So it now approaches the asymptotes right and left instead of up and down, but the domain now is the same as the range over here in that it is all reals. So let's write that over here. And the range, because of our principal interval, is now only from -π/2 to π/2. So that's different in that the domains and ranges don't switch exactly. That it becomes the principal interval. So let's look on the unit circle and see where the principal interval is for tangent. So, and again, those are open circles, but that's on the unit circle. That's where the principal interval is. So for any inverse tangent problems you might have to solve, those are the only outputs you can get for an inverse tangent. The only angles you can put in for an inverse tangent, just so that the functions are one-to-one, and that's inverse tangent.
Should we put bloopers in our video?
No.
Quite a few, actually.
So, right now I'm here to talk to you about how to do secant and inverse secant. So the first thing I'm going to show you is the secant graph, right here. Now, this is only one period of the secant graph. However, it continues on in both directions. So it would have the same sinusoidal pattern. And it actually follows the pattern. If you were to draw in cosine, then it would go through here and meet in all the same points at 1s and -1s. Except where there would be zeros, there are now asymptotes. Now, there is something called the PI that you have to know that goes right there. And so the orange part is the PI. And when we change this over to an inverse secant problem, you're going to need to know that because it has to use the PI to be a one-to-one function. Now, the domain of the secant is going to be x cannot equal pi over 2 plus pi k. So it cannot equal pi over 2 plus pi k. And the reason for that is the asymptotes that go through, and those are the only places that won't have solutions. Now, the range is going to be from negative infinity to negative 1, and then 1 to infinity. All right? And now we have to put in our PI. So our PI is going to go from 0 to pi because this will make it a one-to-one function. All right, and now we're going to transfer all this over to the inverse secant graph. So here's the graph, and you can tell that it is flipped, and now instead of going up and down, the arrows are going out to the side. There's only one horizontal asymptote, and this does not continue up and down like the last one. So the domain and range, the range is going to be from negative infinity to negative 1, and then 1 to infinity. All right? And now we have to put in our PI. So our PI is going to go from 0 to pi because this will make it a one-to-one function. All right, and now we're going to transfer all this over to the inverse secant graph. So here's the graph, and you can tell that it is flipped, and now instead of going up and down, the arrows are going out to the side. There's only one horizontal asymptote, and this does not continue up and down like the last one. So the domain and range, like this one, will be the same except flipped, so that now the x's replace the y's. And so the range will be, the domain is going to be the same as the range for the secant graph. Cut this out so I don't look like a fool, because I'm acting like an idiot. All right, and then the range is going to be the PI. And you have to make sure that they know that it can't equal inside of here. All right? And now, the only location where angles can be plugged in on the unit circle are going to be from here to here, which is 0 to pi, because that's the same as the principal interval, and it's the same as cosine because it's a reciprocal function. And there you go. That is secant and inverse secant.
This is cosecant and inverse cosecant, which are the reciprocal functions of sine. So for cosecant, it has a domain of x cannot equal pi k. And we express it this way because it has asymptotes at every pi k. Okay, k is representative of any integer. So like, for example, 1, 2, 3, and it just continues out in any direction. And so for its range, it has a range of negative infinity to negative 1. And the negative 1 is bracketed, but the infinity is a normal parenthesis. And then it goes from 1 to infinity. And so that is the range of cosecant. Now for its inverse, it also, again, is a one-to-one function, and they restrict its range, or the range of that, but the domain of the original function to make sure that it remains one-to-one. And so its domain is from negative infinity to 1, just like the range of cosecant, or negative 1, excuse me, unison 1 to infinity. And so it's just the exact opposite of the range of cosecant. And now its domain, or its inverse cosecant's range, because it's restricted, only goes from negative pi over 2 to 0. And unison to 0 all the way up to pi over 2. But that's As for its unit circle, it has the same range as sine, so it is in the same spots, and it goes all the way around, just like sine. All right, and so that's cosecant and inverse cosecant.
Hi, it's Andrew again. I want to talk to you a little bit about inverse cotangent. So we've talked about some others, but inverse cotangent, originally normal. This is normal the cotangent graph, which is the reciprocal of the tangent graph. So you see it has its asymptotes here, where the tangent graph has its zeros, and it has its 0 where the tangent has its asymptotes because of the way the reciprocals work. And you see that it's decreasing again because it is because it's the reciprocal of the tangent. We see that it has these specific values here. So let's look at our domain and range. So our domain is going to be all numbers except, of course, the asymptotes. So we want to make sure that we put that x does not equal the asymptotes. So let's put here x does not equal pi k. And our range is, again, as you see, because it's approaching the asymptotes, it's going to be all reals. So that is our cotangent graph. Now, again, to make an inverse cotangent graph, we want to make sure that the inverse is a function. So we got to make sure it's one-to-one by limiting it with the principal interval. So our principal interval here is going to be the period we wrote here, which is 0 to pi. Let's put that down here. And again, it's parentheses because it is the asymptotes. 0 to pi. So that 0 to pi principal interval is going to transfer to our range here. So as you see, this is the inverse graph. All the x's and y's are flipped. So let's write the domain and the range with this as the new range so that it is a function. The domain is all reals because it approaches the asymptotes. So there's our graph for inverse cotangent. So let's look on the unit circle and see where this is. So we've got, sorry, orange. We've got 0 to pi. It's right here. Right here. So again, make sure that all of your angle values are within that range so that it is a function. And that is inverse cotangent. Hi, I'm Andrew Darling. I'm going to explain math now.
Hey.
That was like weird.
And there you go. That is secant and inverse secant.
Oh my God.